What's up, gangsters? This video is probably not going to be for you. And I say that because this is 3D printing content, and worse than that, this is very narrowly focused, nerdy, and detailed 3D printing content. It's really only for those of you who if you already own a printer, you might find this interesting. There's one particular part of it that I hope even veteran 3D printers will watch, and that's why the term bloom is incorrect, but I'm getting ahead of myself. This is really more towards guys who are trying to figure out how to tune in or dial in their 3D printer, whether they've owned it for a long time, whether they've just bought it and this is their first time out of the gate, or if they're thinking about buying one and want to know what it takes to get one tuned in order to make super cool little tiny scale modeling parts. So, yeah, it's going to be long and it's going to be exhaustive, but it is what it is. So without any further lip flapping on my part, let's get right into it. Okay, so here is the new printer, and you can see that I have already started using my super sophisticated build tracking methodology, the Sharpie 9000 technology. And for me, the reason I do this, it just got to be a habit from the old machine where I had so many fails. And for me, what differentiates an X from a hash mark is really just whether or not it sticks to the plate. And the build quality itself, like did all the features print properly, etc., that's for later. I just wanted to track whether or not I had stuff sticking to the plate because it was, such a crapshoot with the old machine. But you can see, the first one was a fail, and I changed one setting and then got all this. Now, this is not all the same settings, not all the same print, but that's what I'm going to talk about in terms of calibrating, and that's really not even the right word. It's not calibrating, it's just dialing in this little machine to get some super successful results. You'll also notice, if you're sharp-eyed, that I have a new bottle of Anycubic Craftsman Gray here. They're calling it DLP Craftsman now, but honestly, it's the same stuff as far as I can tell as the old Anycubic Craftsman. Just like the Frozen Aqua 8K that's in here now is, I think, the same as the old Frozen 4K or whatever. It's just silly to think that the number of K in your display has anything to do with the resin. It all cures at 405 nanometers. So anyway, it is what it is. But you'll also notice that this is the Mars 4 Ultra. I went into more detail in my previous video, but I know some of you are going to wonder, why did I get the Mars 4 Ultra instead of the Mars 5 Ultra that's just come out? In simple terms, I did not want some of the new features that are on the Mars 5 Ultra. They just don't interest me. And I talked more about why on the other video. But I'm super happy with my choice. I needed a small format printer to fit in this space. So I did not want to get a Saturn. I also just don't print stuff that's really big enough to require a larger machine. Okay, so as you can see, this piece of software is called Lychee Slicer. And if you're not familiar, a slicer is the software that's required between the creation of the STL file that you're going to print and the actual printer. It does some things that are absolutely required in order for you to be able to get to an actual printed part. And I'm not going to cover all of that stuff in detail, but let's just throw a part in here so that you can see kind of what happens when you do that. All right, when the part first drops in, it's basically just sitting there on the build plate in whatever orientation it's in. And it's up to you now to correctly orient the part and add supports and dictate what kind of resin and what settings you are going to use. And that's the part that we're going to be talking about, is the settings. But before we do that, let's just open a lychee scene that shows a part that's completely set up so that you have a little bit better idea what that's going to look like after you do all that work. Okay, so these are a couple of parts, and we're actually going to see these parts again in the discussion here in a few minutes. But this is what it looks like after the parts are oriented, the supports are added, and then the last part that you do is you do the export. And it'll tell you over here how long the print's going to take. And this is where you set up things like anti-aliasing. And again, not going to get into the discussion of what that's all about right now. But you can see that the resin specified is frozen aqua 8K gray, 10 microns. And what that's saying is that that's this particular resin, and it's going to print in 10 micron thick layers. Now, how does that all get decided? So right here, you have this resin tab, and you can see that I have a selection of resins and layer thicknesses that I already have set up to choose from. Okay, so if I start with, and for these parts, these are the kind of parts that I would typically print at 50 microns because they're not detail parts. You can see that when I go in here and edit that I have a whole bunch of numbers. And these can get pretty confusing and overwhelming in a hurry. But let's just go through the most important ones, all right? The very first thing is layer thickness, because everything else is going to be basically dictated by that. And you can see here that 0.05 millimeters or 50 microns is what I've set. But you'll also notice over here that we've got two kinds of layers. We've got burn-in layers and we've got normal layers. Okay, so we'll talk about the burn-in layers first. The burn-in layers are basically the initial layers in the, some people like to call it the raft. Basically, it's at the very foot of the part, down here, where all of these little round discs are. That's the footer, the foot. If you make a specific raft, whatever it is, it's the first thing that gets printed, and it's what sticks everything to the build plate. And it's sometimes a good idea to expose those first few layers at a much hotter exposure time, in other words, a longer exposure time, than you would use for the rest of your layers, so that you can make sure that it sticks, because that's the first most important thing. If it doesn't stick, well, you know, nothing else good is going to happen. So I use 10 burn-in layers, and I'll talk about the setting here for the exposure time on the burn-in layers. But that's basically when I showed you my tally of success and failure, that first one that failed because it didn't stick, my exposure time on the burn-in layers was the default of only 25 seconds. And it didn't stick, so I went back to my old exposure time for burn-in layers from my old machine, and I just adopted that, and it worked fine, so I'm sticking with it. Some people might say, oh, the 50 seconds, it's way too long for a burn-in layer time. I mean, is it really? It's 10 layers, it takes 500 seconds, and if it ensures that the build sticks to the plate, then it's all good. And some people might say, well, that's going to make it really hard to get your parts off of the build plate. I just haven't found that to be true. In fact, with this new Mars 4 Ultra and the texture that's etched into the build plate, they come off of there super easy, even easier than in my previous machine, and I didn't find them all that hard to get off with that one. Anyway, so these are my burn-in layers. This is the exposure time. Some people like to use transition layers, and that's where it basically steps down from this exposure time to this exposure time over here. I've never seen much difference, so I don't use any. All right. So that's the first and most important thing. These values are pretty much going to be set for you as a default, and you can adjust those if you want to. Again, this is something that's going to have relatively little importance compared to things like exposure. And so I don't particularly mess with those unless I feel like I have a really compelling reason. All right. So then let's jump back over here to the normal layers. You can see that those only expose at 1.8 seconds on this particular setup for 50 microns. All right. Then if we go down here, there's a variable called wait before print. This is what I consider to be the second most important variable, and we'll talk about why that's important when I go to actually show you the parts. But right now, this set of parameters is different from what comes stock, so to speak, because every resin, if you go and add a new resin, it's going to come with recommended parameters, and you can change them if you choose. So the only ones that I've changed in this entire setup are layer thickness, exposure time, wait before print, and then the same thing over here. I changed the lift distance, but I'm not even going to get into why I did that. It's really has to do with this thing here, the two-stage motion control, which I'm not gonna talk about too much. Basically, with some of these newer machines, it gives you the capability of doing the lift and retract in 2 stages, so that part of it happens really slow, like normal, and then the rest of it happens super fast. And the idea is that saves you time in the build. I don't really care about that. So I just have basically turned the second stage off by setting it to 0. And you'll notice that the total of the retract distance, and it's automatically doing that in 2 stages. There's really nothing you can do to prove that's a default. The total of that is equal to the lift distance. And basically this is what happens then when after the layer is exposed, the build plate raises up 10 millimeters, and then it goes back down 10 millimeters. So that's really all that is. Lift speeds, I'm not even going to really get into that much. I don't mess with it unless I feel like I really have to, and I have not with this setup so far. Basically, my philosophy when it comes to these parameters is only ever change one of them at a time, and don't change anything that you don't know you really need to change. Okay, so that being said, once you've got all of these parameters set, then when you go back over here to export, then if you change something, it's going to give you a blank right here, but you just jump back over to prepare and then jump back to export, and you can see that now, because we went from a 10 micron layer, which is the thinnest, to a 50 micron layer, that the build time dropped by about a factor of 5, as you would expect. And now, even though this is about 2.5, 3 inches tall, it's only going to be about a 6-hour build. So there you go. That's just a basic overview of what the slicer is and what it does. Lychee is just one slicer that's available. The other popular one that you'll hear about is called Cheetahbox. But you don't really have to use either one because most of the manufacturers make slicers of their own. It just happens that these specialty slicers, I think you could argue that they work better, and that's why they're more popular. And my personal choice is Lychee, even though, especially with the latest versions, it's probably really not a lot different from Cheetahbox. So there you go. Now let's go take a look at the actual parts and see how they were affected by my choices in the slicer. Okay, let's talk about the parts that I printed and how I used them to get the machine dialed in for this particular resin. Now, ignore these for the moment. We'll get to that. So as I said, the very first part that I tried to print was a fail. It did not stick to the build plate. And what it was this little set of 1/32 scale parts that I designed and printed for another project. And I was trying to print these at 20 microns, and it just failed. So the only thing that I changed in going from print number 1 to this successful print number 2 was I doubled the burn layer time. And as I said, some people think that that's excessive. Like I had one guy on Facebook tell me this morning that I was using excessive burn layer times for no reason, and that I was burning out my my screen unnecessarily, which is exactly as I said when I was recording the part where I went through the parameters. Look, the bottom line is a print that won't stick is what's really a waste of time. And if I can make them stick consistently using, by frying the fuck out of those burn layers, that's what I'm going to do. So the second print, literally the only thing I changed was the burn layer time. The exposure on this was 2 seconds. And I did that because, even though, if you're just starting out, the best thing to do probably is to run calibration parts like these. But I knew the ballpark. I have enough experience to know about what kind of layer exposure time I needed for this resin. And so I just went for it because I needed these parts. Somebody had ordered some from me. I wanted to get them in the mail. And so I just went for it. And then when I changed that one parameter, again, going back to changing only one thing at a time, unless you really understand what each parameter does, is always the right thing to do. And my second print was successful, just fine. But when I looked at it, I thought, well, it's maybe a little bit hot. So I sort of filed that away as I'm going to come back to this to really dial it in for 20 microns later. But I wasn't ready to start doing that yet because I had another part that I needed to print, and it was the thing that I showed you here. And this one, when I was going to run at 50 microns, and again, I knew kind of what the ballpark was. And so I just set it at, I think, 2.5 seconds, and I ran it, and not only did it stick, but for the most part, you can see that the print looks really good. I had some engineering changes to make, so I printed it a couple of times, and this was actually, I think, the third version of this part. But you can see that the surface finish is really nice, okay? Even on those flat parts, on this end of it, looks really good. And I was happy with it, but I was showing it to the guys in my little print think tank, all of which are pretty advanced hardcore users and very picky. And one of them said, yeah, what about all of those lines on the sides? Those shouldn't be there. And I was like, yeah, well, you're not wrong. They shouldn't be there, but I'm not really fussed about it because they're not a big deal. A little bit of primer, a little bit of sanding, and this is not a part where a perfect surface finish is really that important. This is a full-size actual engineering part, if you will. What I was concerned about was the accuracy of things like these holes, because this part fits with actual metal components. And so I was like, yeah, I'm not too worried about it. But of course, because, us being us, somebody said, well, I bet if you stand that thing straight up, it would be better. And this is, look, I know some people are going to look at this and they're going to want to talk about supports and orientation, and that's not what this video is about. But I will say this, most of what you see online about orientation is horseshit, especially if you see people telling you to use some kind of arctangent trigonometry formula to calculate it down to any number of decimal places. It's just, look, it reflects a lack of understanding about the way that resin 3D printing actually works. This is at some angle close to 45, obviously. I couldn't tell you exactly what because I oriented it with my eyeballs. And you can see that the surface finish, as I said, is just fine, except for that. So somebody said, well, I bet if you stand it straight up, which of course, some people are freaking out about that because they believe that you should automatically angle all parts. Somebody said in the group that if we stand it straight up, that it'll eliminate those. And I was like, well, maybe, maybe not. But the reasoning is that even though I've got a pretty straight load path between the part and the build plate, which is always the number one consideration when arranging your supports, and honestly, I don't like that it automatically puts this little angled tip on them. Ideally, these should just be straight to the part. The reason that it puts this angle on them, though, is so that the tip is going at a right angle into the surface and you get a smaller contact patch, which is valid. But if you're not concerned about that, you can use a straight vertical support. Anyway, I thought, all right, well, let's just try it. Let's just see what happens. And so I set it up like this, and I put these on there just to make sure that it really was not going to be able to rock back and forth under peel force, because that's really the theory here, is that peel force might be causing it to just wiggle a little bit with each layer separation, and that's what's causing those. And that's, not a bad theory. So we can test that pretty easily by just running it in a different way. And you can see that it, in fact, did not solve the problem. It's a little bit tough to see. It reduced the effect, but it didn't solve it. And what you should really take notice of, hopefully this will show up on camera, is that even though the effect is less, it's still correlated to this larger cross-section. Okay, if you look, there's more of it right here, there's more of it right here, there's more of it right here, more of it right here. Same thing on both parts. And that's kind of like what you see with volumetric shrinkage effects in injection molded parts, where you've got a change in cross-section. Like if you have a rib intersecting a sidewall of a part, you may see a sink mark on the outside of the injection molded part because the rib on the inside is too thick. This is, so this kind of looks like a similar sort of thing, albeit maybe in the opposite direction. But I sort of just filed that away. I was like, all right, well, I'm okay with it if I can't solve it. Oh, wow, I just noticed on the inside of this part that it's got some goobers in there. I never saw that. That would be a bit of a problem for the shaft that has to go in here. Anyway, so I kind of filed that away because I thought, well, it's not too bad. I checked the test fit on the shaft. This would be a usable part, just like it is, but certainly with a little bit of primer and sanding, and it is going to get painted. So set that aside. Oh, and I also had on the same plate these little tiny parts, and I was seeing this effect on the support, okay? And on the vertical face there, a lot of the same type of lines. And that's really worse, even though, again, easy to fix with primer and sandpaper. I definitely did not like it. But I thought, well, maybe I just need to dial in my exposure time, and so let me just work on that. So I started printing test coupons. And this is the Photonsters validation test part, and I really like this one for a couple of reasons. One, it gives you good visibility to features that should be sharp. It's also very thin, so it prints very fast. At 50 microns, this takes like 15 minutes to print. But I also like it because when I downloaded it from Cults, I also got the Fusion 360 file, and that enables me to take a close look at what actually should be here and understand what the dimensions are. Like those letters right there where it says validation, those are 0.3 millimeters tall. So I can look around and see exactly what I should be, what it should be, and correlate that to whether or not those features are successful. Okay, like over there on the right-hand side, it's got those little fins and slots that are 0.05 millimeters wide. And that's getting down to lower than what I would expect to be successful, because really 0.1 millimeters is kind of what I consider to be the practical limit. So if it fails right there, I'm not concerned about it. But where it goes up to 0.1, I'd like to start at seeing B. I'd like to start talking more betterer. I would like to start seeing it be more successful. So I took a look at this, and this was exposed at 2 millimeters. 2 millimeters. Good Lord, I can't even think or talk straight this morning. At 2 seconds, all right? And you can see the layer lines there at 50 microns, and you can see that there's something there that should be there that's not really successful. And one thing that I noticed in particular, let me get a pointer, is in this area right here, I'm seeing that the edge right here of this square is not straight. It's sticking out a little bit more right here in particular. And I thought, that kind of reminds me of the effect that I was seeing on this thing, where there's a larger cross section, because it's happening where I go from the thinner or smaller cross section right here to the larger cross section over here. So I sort of filed that away. What can I do about that? All right, but where you're really looking at on this part is in places like this, where you've got this intersection. That ideally should be very pointy, and you can see it's not. It's muted as it crosses over. Same thing down here where you've got the fin and the slot. So I know this is overexposed. That's the point. So on my second one, I dropped it down to 1.8 seconds, and that looks significantly better. Still seeing the layer lines. Of course, you're going to see those. But it does look better right here. But I've still got this issue with this edge not being straight either here or here. So I'm like, all right, well, I'm getting, my exposure time looks pretty good, but let's go down a little further and see what happens. So with this one, I saw some improvement right there. Still seeing, however, this issue with the edge, and this is not really hugely better, and I'm seeing some delamination effects here that tell me that it's a bit underexposed. So I'm like, all right, 1.8 is not bad. Maybe I could go down to 1.6, but yeah, I'm gonna kind of quit fussing with the exposure time and see if I can solve this problem right here. Okay, so now we're going to get into the parameter called wait to print. It's called light off delay on some machines, light on delay, whatever it is. Basically, what it is when the build plate is coming down and it arrives at the correct place according to the layer thickness that you've specified. So in other words, in this case, it's 50 microns above the film. There's the distance between the film and the previously printed layer is 50 microns. And obviously, in that space, you have liquid resin. And you've got the build plate or the part trying to push that liquid resin out from in between it and the film. And if that resin is still flowing when the light comes on, you're basically going to be curing resin that's still moving. And what the light on delay or wait to print does is it says that rather than turning the light on as soon as the plate stops, you're going to wait for a specified time and give that resin to be squished out from between those two surfaces. And hopefully it'll not be moving when the light comes on. All right. And so I turned on the 1 second light on delay, and I immediately noticed with this test that this edge, you can see, is quite a bit straighter. It's much better. I'm like, aha, this is good news. And everything else looked better as well. When you compare the two, all right, it's readily visible what the difference is. So I'm like, all right, I'm onto something. So again, because I'm changing one variable at a time, I stay at 1.8 seconds, but I increase the light on delay even further. And look at that. That is a pretty spiffy print. Pretty happy with that. It's obviously still not working right here where this number or whatever it is, but we'll get to that. So at this point, I'm happy with that, and I'm thinking, I'll bet that this effect that I'm seeing here, going back to these parts, is the thing that will solve those weird lines on the sides of the part. So I reran it using these exact parameters, 1.8 seconds, 2 seconds of wait to print or light on delay, and look at that. Look at how nice the sides of that part are. So by analyzing the effect and attacking the appropriate variable one at a time, I now got a really beautiful print. You can still see there's still a little bit of weirdness right there. But again, you know, if you don't see something like that on one of these resin prints, it's honestly surprising to me. You have to remember, this is junk technology that basically runs on junk equipment. It's the cheapest components available, and it's in a machine that basically is taking the part and gluing the shit out of it to the film and then ripping it apart and repeating that 1,000 times or however many it takes to produce your part. I mean, it's not exactly complicated, and you're dealing with a process that's a little bit dependent on nature and therefore is going to be a little bit chaotic. So sometimes you're just going to have weird things like that, and there's honestly no point in trying to chase that out. But you'll see guys do it. They'll start screwing with all kinds of variables in order to fix something. And for me, there's a point of diminishing returns where as long as the part looks good, fits right, works well with minimal amount of cleanup, then you're good. Okay, before I move on, I want to go back to this problem right here where we see this problem with the edge and this cross section. There's a lot of people who are going to refer to this as bloom, and that's just not right. And let me explain why. So, got to take you into the Wayback Machine. When I did my graduate mechanical engineering work at Texas A&M, I can't believe it, almost 30 years ago now, my research project was in rapid product development using the very then bleeding edge technology of 3D printing. And my first job after grad school was with DTM, which was the company that developed selective laser sintering. If you're not familiar with SLS, it's basically the process of using a laser beam to fuse powdered materials that will melt, like nylon, acrylics, even metal. And even now, that technology has continued to evolve. And even though DTM is no longer around, there are still companies that are producing machines that do amazing stuff with SLS. If you want a real works-like prototype instead of a looks-like prototype, and you need to have real material properties, SLS is pretty much the way you got to go. But and part of anyway, the point is that part of my job was to go all around the world and teach people how to use that technology. And a lot of those customers also had the original laser-driven SLA machines produced by 3D Systems. And bloom, even then, 30 years ago, was a term that was pretty common. And basically what it refers to is energy bleed when you use a laser. Let me draw you a little picture to explain. So a laser beam has a certain spot size that it varies according to the amount of power that you set it to. And you can think of it as a round circle, but it's really not a round circle. A laser beam is a lot more like a tiny airbrush than it is a paintbrush, because there's a heat affected zone all around the spot where material is where it's kind of like overspray, where material is being partially melted or partially cured outside of the actual spot. And you can't really control it. You can compensate for it. In fact, the old DTM SLS machines, and probably the new machines too, had a setting called laser beam offset, where you would essentially move the spot over by some amount to compensate for this heat affected zone. Because basically what that does is it makes the part a little bigger than you intended it to be if the spot is running along the, like if the boundary of the layer is right here, then obviously you're going to have some overcure because the spot is extending outside of that. But if the boundary of the layer is right here at the edge of the spot, you're still going to have some material outside of the intended boundary. And so you could compensate for that. Now, I know at this point, you guys are like, but dude, like this machine, your little Mars 4 Ultra doesn't use a laser, bro. Yeah, I know that. But here's the thing. This overcure effect, this energy bleed effect happens whether you provide that 405 nanometer wavelength light with a laser or by lighting up a pixel in your display screen. And so if you think about a single 18 micron square pixel, or however big your pixels are, you're going to have this energy bleed all around it. And so if you think of a voxel as a pixel with height, with volume, it's going to look more like a little loaf of bread than a Lego, okay? And that's just the reality of this process. And this amount of overcure, the distance between the edge of the pixel as far as the software and the firmware understand it, is that distance. And that distance is going to be consistent, whether it's all the way around the edge of this whole square or whether it's around the diameter of one of these little circular parts or around the inside of a hole, whatever it is, that blooming effect is going to be a constant amount. And that's the difference between bloom and what's going on here. Because what's going on here is that the amount of oversize is dictated by the size of the cross section. Because what's happening is that this is material that's being squeezed out from between the part that's attached to the build plate and the film. You've got liquid resin that's trying to flow out from between those two surfaces when the plate comes down. And the reason that you get this oversize is because if the light turns on, as soon as the plate stops moving, the liquid resin is still moving and you're basically curing resin that's moving. And when there's more of it, as there is in a larger cross section, it's going to result in a greater error around the perimeter of that. So this cross section is going to be oversized more than this cross section, or this little skinny cross section right here. And so what I want to propose is that we stop calling this bloom, because that's just not what it is, and that we have a new term. And I like the term squish because basically what we're trying to do is squish the liquid out from between the previously printed layer of the part and the film. And that's why light on delay, or wait to print, whatever you want to call it, solves that problem, because we're giving a specified amount of time between when the plate stops moving down and the time that the light turns on to allow the squishing to take place. So that's my case. Okay, so once I got satisfied with what I was doing at 50 microns, it was time to go back, or forward, I guess you could say, to 20 microns. Because while 50 is kind of the default, and I think honestly the easiest, and it's great for parts like this, if you want to do itty-bitty scale modeling parts that have a lot of detail, 30 microns is kind of the maximum in my opinion, and 20 is even better. And I was able to produce good prints at 20 microns even on my old printer that was not so dependable. And you can see why 20 microns works pretty good. And I immediately lowered the exposure time to what I thought would be a reasonable range. It's not linear, like, you know, we're not going to go down by 2.5 times since we're going from 50 to 20. I dropped from 1.8 per layer to 1.5 per layer. And I increased the wait to print to 3 seconds because I figured, yeah, you know what? Let's just make really sure that that's working. And this 20 micron print is really pretty nice. You can see how crisp the junction is in the middle of this area right here. It's really nice. And it's really pretty good on the letters. But there were still some areas where I felt like I might get a little bit of improvement. You can see, like, look between the I and the N there on resin, and you can see the inside of the P is filled in, the inside of the A. You know, it's just stuff like that that kind of makes me feel like it's a little bit overexposed yet. But look at the difference in the layer, in the visibility of the edges of the layers in this real slightly sloped section over here on the side. Like right here, that number didn't even print. And you can see those layer lines. Now look at what it looks like at 2.5 times more layers. It's just really, there's just really no argument there in going, down to 20 microns. So I'm all right, I'm moving in the right direction. I'm doing pretty good. Let's see what a slightly lower exposure time produces. And now, when you look in those same areas, we've got space between the I and the N. The insides of the letters are a little bit more defined. And overall, this just looks pretty good. I'm not mad about this at all. And so I decided that this was probably going to be, at least for now, a good baseline default setup for 20 micron prints. I'm pretty happy with that. But the real goal has always been, for me anyway, to get down to 10 microns. Oh wait, I forgot to show you print number 8. I went down to 1.1. This is where I landed as my default. I mean, look at how it's really nice when you got the sun, as long as you get it at the right angle. Look at how crisp those letters are. You can really see the insides of the P, the A, the D. Got space between all the letters. That junction there is pointy. So this was my default. 1.1 seconds per layer and 3 seconds of wait to print or light off delay, whatever you want to call it. So with this, I felt really good because I'm like, okay, I got a very solid 20 micron setup that I can use for a lot of stuff, but I really want to be able to go down to 10 microns, partly because, again, twice as many layers. There are surfaces like this slope where if I could get rid of those layer lines altogether, wouldn't that be even nicer? Plus, my friend Tom Anish is constantly showing us prints in our little group from his, as he calls it, his bestie, which is his Frozen Sonic Mini 8K that regularly produces beautiful prints at 10 microns. What's kind of striking though is he calls it his bestie because his other Sonic Mini 8K won't do it, and none of his other machines will either. And this is kind of the thing. This is part of why I say that this is junk technology running on junk equipment, because there's one thing we've seen in our little group is that there is inconsistency not only between brands but within brands. So at any rate, I really was like tired of Tom showing off, and I really have wanted to get to 10 microns. So I went to 1 second exposure per layer, 3 seconds of light off delay, and look at that. Look at how beautiful those letters are. Look at how pointy that is. Look at that. That is just crispy and delicious. Just like Popeye's fried chicken. Yep, look at that. That number, which is only sticking up 0.1 millimeter from that surface. Very nice. But here's my favorite thing. Look at the difference in this sloped surface. Hopefully I can get the angle right and you'll be able to see it. I don't know, it's kind of challenging to get the sunlight just right. Okay, there you go. You can see the layers on the 20 micron side. There they are on the 10 micron side. Look at how fine those layers are. I mean, they're there, and that probably will start to show under a coat of primer, but it isn't going to take much to fill those in, and certainly not much to brush them off with a little bit of sanding. So I'm thrilled. Like, I figured that this test coupon would be where I would start to see a failure if there was gonna be one. And so I'm thrilled at this result. This is really, really good. So, but okay, so yeah, that's all wonderful, but coupons are just coupons. These are just test parts. They don't really do anything except help you establish a good operating baseline for your machine. The goal, of course, is to print real parts. So I decided, both literally and figuratively, to just send it, as we used to say in the motocross world. Literally, because the Mars 4 Ultra has Wi-Fi, and that's part of what's made doing all of these so easy and fun. Is I don't have to use SneakerNet to carry the file to the machine on a USB drive. I just hit the send and print button in Lychee, and away we go. And so that's what I did. I sent and I printed. And these are all 10 microns. And this is 3D printing porn right here. So if you need a moment, if you need to go get some lotion, I would understand. So let me show you what's on here. This is kind of a smorgasbord of greatest hits. Okay, so maybe the third time will be a charm. I shot this in the sun, and it was terrible. Toads fail. So then I shot it again without the sun, but still on the build plate, and that was just practically unwatchable, because moving the build plate around smoothly was just, beyond my meager camera handling abilities. Anyway, but I did want to show you this. Remember that 50-second burn layer time that was going to make it so hard to get parts off the build plate? Yes, number 22 scalpel blade is the way, my friends. Anyhow, so now that I've got all of these off of here, let's look at each one of them individually. So we'll start the way that they were on the plate. This is the seat that I designed for my 1/32 scale Hasegawa P40 a few years ago, and I've never printed it at 10 microns. Never been successful at that. So yeah, I'm pretty thrilled. You can see all of that sweet rivet detail. Get over here under the light a little bit better, and you can see like all of the stiffeners there just came out really good. The whole thing just really good. So yeah, that's fun to see for the first time at 10 microns. This that just went on the floor and demonstrated why it has this protective cage around it. Yes, yeah, that saved something nice being broken. Anyway, this is 1/48 scale. This is the R1830 Pratt Whitney Twin Wasp, designed by John Colasante, and I think you can buy this from him at Matters of Scale. He is not only just an awesome guy, but he's a really good Fusion 360 and Blender guy, and a great printer. And I've printed this file before, but only at 20 microns, and it's just fun to see it at 10. Really, what's cool is if I get the angle right, you should be able to see down inside there by the reduction gear housing. It's really tricky to get this at the right angle, but the Pratt Whitney text on the ignition ring down there at the base of that housing. I hope you guys can see that, because it's just so cool. Like, you almost need a magnifier, there it is, to see it. But it's kind of the acid test of print resolution. That's that 18 micron square pixel that is one of the main reasons that I bought the Mars 4 Ultra. So those are super cool. This little seat is 1/48 scale Hurricane seat with seat belts from the guys at Arma that you can download from them. You can get it in the with the little box and supports and print it that way, or you can add your own supports. But either way, it is really, really just wonderful. I've actually got one just like it right here from my old machine, printed at 20 microns, and that is in Anycubic Craftsman Gray. And I think you would agree that it's not bad right here, but it's just not quite as good as this new one is. So there's that. The next thing over was this tire from Tom Annie's for the Kotare 1/32 scale Spitfire. And you can see the lovely text on the side of the tire. Really, really nice. Then next to that were some more tires. These are 1/72 scale Mustang wheels and tires, also from the guys at Arma. And that's just super cool to be able to see the raised lettering on the sidewall of the tire. Even I think there's a valve stem in there. So much fun. All right, the next thing over was this propeller shaft. This is from Tom's 1/24 scale detail up kit for the Airfix 1/24 scale Hellcat, and the propeller shaft with the splines. And you can see there's a little bit of a weird line running across that. That's one of those random defects. And, what are you going to do? Reprint it? I personally would stand this little shaft up straight if it were me. And you can get the parts from Tom either already supported or not. All right, next thing over, there was another one of these tires. Then again with the little landing gear controls that I created for the Kotare Spit. And these, look, the 20 micron ones were good, but these are just that extra little bit better. You can really see the inset in the lever there. You can see just really good. Nice detail. All right, then the next thing over is back to Tom's 1/24 scale parts for the Hellcat. This is kind of another one of those acid test parts, because with it being curved like that, any thicker than 10 microns, you're going to see some places where you get layer lines, especially right here on the top of this part. That sort of concave round thing right there by the number, that thing will show layer lines readily at 20 microns. And at 10, none. And I am just stoked because Tom has printed this part and shown it to us many, many times. And we've all been super jelly of how good it looks at 10 microns, and yeah, I'm happy that mine looks just as good. All right, this is another one from his 1/24 scale set, the ignition ring for that, and you can see how nice and crisp that Pratt Whitney text is. Yes, and all the holes that are there for you to plug ignition wires into. Super good. All right, last thing are the wheels for the 1/32 scale Kotare Spitfire to go with those tires. And this one is a great justification for 10 microns because these wheels are dished, and they will definitely show layer lines in that shallow dish at 20 microns. And there at 10, nothing. Just super cool, super crisp. All these parts are just fantastic, and I'm so happy. In fact, I gotta say it, I'm kind of happy the old machine broke. Okay, so there you go. As promised, detailed, long, nerdy, but hopefully helpful if you're trying to figure out how to get the best out of your resin SLA printer. Could cover a lot of stuff, but there's lots and lots of videos out there, obviously, about 3D printing and how to do this stuff. And I'm not claiming that this one's the best, or that I'm the best, or that I know more than everybody else. But the one thing that I don't really see much is what I tried to present here, which is just a really nitty-gritty, step-by-step process for dialing in your machine and showing the results along the way, and how you use those results to make decisions about what settings you want to change. So anyway, yeah, still before noon, and I can't think or talk straight. So anyway, I really hope it was useful and informative, and if you suffered through the whole thing, as always, thank you and much love.